There's a place so far from Earth, so shrouded in darkness, that even our most powerful telescopes struggle to pierce its secrets. Out beyond the familiar planets, beyond the icy grip of Pluto, lies a realm of cosmic oddities, the Oort Cloud. This vast, mysterious shell of icy objects marks the very edge of our solar system, a place where the sun's light is little more than a dim flicker in the endless night. And here, hidden in the shadows, drift some of the strangest objects humanity has ever discovered. We're talking about rogue planets with orbits that defy logic, icy bodies that shouldn't exist, and maybe, just maybe, clues to forces we don't yet understand. Imagine standing on the edge of a cosmic cliff, peering into the abyss of deep space. What you'd find wouldn't just surprise you, it would rewrite everything you thought you knew about our corner of the universe. Some of these objects move in ways that make scientists question the laws of physics itself. Others might be visitors from other star systems, hitchhiking through our neighborhood on journeys that began light years away. And then there are the enigmas, the ones that don't fit any category, the ones that whisper of mysteries we haven't even begun to solve. This is a journey to the furthest reaches of our solar system and beyond, where the rules seem to bend and the unknown reigns supreme. Over the next 25 discoveries, we'll uncover bizarre worlds, encounter objects that challenge our understanding of space, and maybe even stumble upon hints of something unexpected. So buckle up. We're about to venture into the darkness where the ordinary ends and the truly extraordinary begins. The Oort Cloud and the wonders lurking beyond it are waiting, and what we find there might just change the way we see the universe forever. In October 2017, astronomers spotted something streaking through our solar system that defied all expectations. It wasn't a comet, it wasn't an asteroid. It was our first confirmed visitor from another star system, a bizarre, elongated object later named Oumuamua, a Hawaiian word meaning scout from the distant past. Shaped like a cosmic cigar, this interstellar traveler tumbled through space at dizzying speeds, leaving scientists scrambling to explain its strange behavior. What made Oumuamua so extraordinary wasn't just its origin, though that alone was groundbreaking, but the way it moved. As it hurtled away from the sun, something unexpected happened. Instead of slowing down as expected, it accelerated as if pushed by an unseen force. Comets usually speed up like this when their icy surfaces vaporize, creating a visible tail. But Oumuamua had no tail, no coma, no obvious signs of outgassing. So what was propelling it? Theories exploded across the scientific community. Some suggested hidden pockets of gas erupting from its surface, a mechanism never before observed in such an object. Others proposed even wilder ideas, like the possibility of a thin, reflective sail of natural origin catching sunlight. But then came the most controversial hypothesis: could Oumuamua be artificial? Could this oddly shaped, oddly accelerating object be a piece of alien technology? The truth is, we may never know for sure. By the time we spotted it, Oumuamua was already racing out of our solar system, too faint and too distant for further study. What it left behind was a trail of questions, ones that continue to haunt astronomers. Was it just a strange rock, a fragment of a shattered exoplanet? Or something even more extraordinary? One thing's certain: Oumuamua shattered our assumptions about what lurks between the stars. It forced us to rethink the laws of celestial motion, to question how interstellar visitors behave, and most of all, to wonder, what else is out there, silently drifting through the dark? And as we'll see, this was just the beginning. The Oort Cloud and Beyond hold objects even stranger, even more mysterious, waiting to upend everything we thought we knew. Where could Oumuamua have come from? This interstellar wanderer's origins remain one of astronomy's greatest puzzles, with scientists proposing scenarios that sound more like science fiction than fact. One leading theory suggests it might be a shard of a shattered world, a fragment blasted into space when a distant planet was torn apart by gravitational forces near its home star. Picture this, an entire world fractured into countless pieces, some flung into the void at incredible speeds, with Oumuamua being one lonely survivor of that cosmic catastrophe. But there are other possibilities just as strange. Harvard astrophysicists once proposed that Oumuamua could be a hydrogen iceberg, a massive chunk of frozen hydrogen gas that formed in the coldest depths of interstellar space. Unlike normal comets made of water ice, a hydrogen iceberg would leave no visible tail as it vaporized, which could explain its mysterious acceleration. The catch: no one has ever observed such an object before, leaving many researchers skeptical that nature could produce something so exotic. Then there's the molecular cloud theory. Some suggest Oumuamua might not have come from any star system at all, but instead formed directly in the chaotic nursery of a collapsing interstellar cloud, a place so alien that it births objects unlike anything we've seen in our own solar system. These dark, frigid clouds could forge bizarrely shaped objects through processes we don't fully understand, creating cosmic oddballs that wander the galaxy for billions of years before we spot them. The debates among scientists reveal just how groundbreaking and frustrating this discovery has been. Some astronomers argue Oumuamua must have been ejected during the chaotic early days of a young star system, when gravitational interactions between forming planets could have catapulted objects into interstellar space. Others counter that its unusual shape, 10 times longer than it is wide, suggests a more violent origin, perhaps from tidal forces near a black hole or neutron star. What makes these theories so compelling is what they imply about the universe. If Oumuamua is a planetary fragment, then star systems must be flinging debris into space constantly. If it's a hydrogen iceberg, then there's an entire class of objects out there we've never accounted for. And if objects can form freely in interstellar space, our understanding of how matter assembles itself might need rewriting. Every possibility points to a cosmos far more dynamic and unpredictable than we imagined. Yet for all these ideas, one haunting question remains: could we be seeing just one example of a much larger phenomenon? What if our solar system is constantly being visited by similar objects, most too faint or fast for us to notice? Oumuamua's brief visit didn't just challenge our ideas about where objects come from, it suggested we might be living in a galactic crossroads with countless strange travelers passing through unseen. The next one could be out there right now, drifting silently toward us through the interstellar dark. Far beyond the realm of familiar planets, drifting through the frozen outskirts of our solar system, lies a world so strange that its very existence challenges our understanding of cosmic mechanics. Sedna. Discovered in 2003, this reddish, icy dwarf planet follows an orbit unlike anything else we've observed. Picture an elliptical path so stretched that at its closest approach, Sedna still orbits twice as far from the Sun as Neptune, while at its farthest, it ventures over 900 times farther out, nearly a light year into the abyss. A single trip around the Sun takes this lonely wanderer roughly 11,400 years, a journey so long that the last time Sedna was in its current position, human civilization was in its infancy. What makes Sedna truly baffling isn't just its extreme distance, it's the way it moves. Normally, objects in the outer solar system are nudged by the gravity of giants like Neptune or Jupiter, their orbits shaped by predictable interactions. But Sedna defies these rules. Its elongated path can't be explained by the known planets, leading scientists to a startling conclusion: something else must have pulled it into this bizarre trajectory. One compelling theory points to the gravitational hand of an undiscovered world, Planet 9. This hypothetical giant, thought to lurk in the distant darkness, could have reshaped Sedna's orbit over eons, slingshotting it into its current lonely path. There's another, even more dramatic possibility. Sedna might bear the scars of a close encounter with another star, billions of years ago, when our sun was still part of a dense stellar nursery, a passing star could have yanked Sedna outward, leaving it stranded in this peculiar orbit. The idea isn't as far-fetched as it sounds. Astronomers have found evidence that stars often pass near one another in their youth, stealing or hurling objects into exile. If true, Sedna could be a fossil from that chaotic era, a relic of our solar system's violent infancy. Then there's the puzzle of Sedna's surface. Unlike most distant objects which appear gray or faintly blue, Sedna glows with a deep reddish hue, suggesting its icy crust has been baked by cosmic radiation for billions of years. Some researchers speculate it might even harbor organic compounds, the kind that could seed life under the right conditions. Yet with surface temperatures plunging to -400 degrees Fahrenheit, it's a world locked in perpetual deep freeze, inhospitable to anything we know. The more we study Sedna, the more questions arise. Why is it so isolated? How did it survive the solar system's turbulent early days untouched? Every observation deepens the mystery, hinting that our cosmic neighborhood holds secrets we've only begun to uncover. Sedna doesn't just challenge our models, it whispers of forces and histories we're only starting to imagine. And if its strange path really was carved by an unseen planet, then somewhere out there, in the frozen dark, an even greater discovery may be waiting. That deep reddish tint covering Sedna's surface isn't just for show, it's a cosmic fingerprint telling a story billions of years in the making. Unlike the pale gray of most icy worlds in the Kuiper belt, Sedna's striking coloration suggests its frozen crust has been cooked by radiation for eons, transforming simple ices into complex organic compounds. Scientists believe this rusty hue comes from Tholen's molecules created when methane and nitrogen ice get bombarded by cosmic rays and solar wind. These aren't just pretty colors, they're chemical fossils, preserving a record of what the outer solar system was like when the planets were still forming. But here's where it gets weird. Sedna shouldn't have much methane left at all. At its farthest point, the feeble sunlight there is barely stronger than starlight, yet somehow this tiny world has held onto enough volatile ices to maintain that distinctive reddish coat. One theory suggests Sedna might be wrapped in a thin blanket of methane snow that periodically sublimates and recondenses, creating a slow-motion weather cycle that stretches across centuries. Another possibility, its surface could be covered in a porous, insulating layer of organic gunk that prevents lighter molecules from escaping into space like a cosmic coffee filter, trapping the last remnants of ancient ices. The composition gets even stranger when you consider where these materials might have originated. Sedna's chemistry resembles some Kuiper belt objects, yet it orbits far beyond their reach. This has led researchers to speculate that Sedna could be a refugee from the inner Oort Cloud, a place where primordial ices have remained virtually unchanged since the solar system's birth. If true, studying its surface would be like cracking open a 4.5 billion-year-old time capsule, giving us our first clear look at the raw ingredients that existed before planets took shape. Then there's the tantalizing possibility of water. Spectral hints suggest traces of water ice might lurk beneath that reddish crust, possibly mixed with ammonia or methanol. While the surface is far too cold for liquid water, radioactive elements deep inside could provide enough warmth to maintain a subsurface ocean, a phenomenon we've seen on moons like Europa and Enceladus. It's a long shot, but if confirmed, it would mean this lonely wanderer could potentially harbor conditions for chemistry that might, under very generous definitions, be called prebiotic. Every detail we uncover about Sedna's surface seems to deepen the mystery rather than solve it. That reddish tint, those stubborn ices, the possible water, they all point to an object that somehow preserved ancient materials against all odds. As we piece together its story, we're not just learning about one oddball world, we're getting glimpses of the chaotic early solar system, when worlds were tossed around like cosmic dice and the rules we take for granted hadn't yet been written. Sedna isn't just an oddity, it's a messenger from a time when our solar system was young, wild, and utterly unpredictable. While Sedna represents one of the solar system's great mysteries, another visitor from the darkness is making headlines for entirely different reasons, a colossal wanderer known as 2014 UN-271. Discovered just a few years ago, this mammoth object is barreling toward the inner solar system, and it's rewriting the rules of what we thought possible in the Oort Cloud. The numbers alone are staggering. Current estimates suggest 2014 UN-271 could be anywhere from 60 to 230 miles wide, making it potentially larger than the famous Hale-Bopp comet by an order of magnitude. If confirmed at the upper end of that range, it wouldn't just be a comet, it would blur the line between comet and dwarf planet, a cosmic hybrid unlike anything we've seen before. What makes this object truly remarkable is its trajectory. Unlike most long-period comets that swing by the Sun on predictable elliptical orbits, 2014 UN-271 follows an extreme hyperbolic path, arcing inward from the Oort Cloud's deepest reaches. When it reaches its closest point to the Sun in 2031, it won't just pass through the inner solar system, it'll barrel straight through the orbital distance of Saturn before swinging back out into darkness. But here's the real shocker, we almost missed it. Despite its immense size, 2014 UN-271 was only spotted in 2021, when it was already barreling inward from over 3 billion miles away. That delay in detection underscores just how little we know about the Oort Cloud's true population, and raises a chilling possibility. If something this massive could slip under our radar until relatively recently, what else might be lurking in the shadows? Theories about its origins are already sparking debate. Some astronomers suggest it could be a pristine remnant of the early solar system, ejected outward during the planet's chaotic formation before slowly falling back inward over billions of years. Others speculate it might have been a free-floating interstellar object captured by the Sun's gravity, making it a cosmic immigrant rather than a native of our system. One thing is certain, as 2014 UN-271 approaches, it promises a once-in-a-lifetime opportunity. When it nears the Sun, solar heat will vaporize its icy surface, potentially creating a spectacular coma and tail visible even to amateur telescopes. But unlike typical comets that put on brief shows, this behemoth's sheer size means its activity could last for years, giving scientists an unprecedented window into the chemistry of the ancient solar system. The coming decade will transform 2014 UN-271 from a faint speck in telescope data to one of the most intensely studied objects beyond Neptune. Every observation could reveal clues about the Oort Cloud's composition, the early dynamics of planetary formation, and the boundary between comets and dwarf planets. One way or another, this mysterious giant is about to teach us just how much we still have to learn about the frozen fringes of our cosmic neighborhood. As 2014 UN-271 barrels toward its closest approach to the Sun in 2031, astronomers are bracing for a celestial spectacle unlike anything we've seen in generations. Given its enormous size, this icy wanderer won't just quietly streak through the inner solar system, it could erupt in a series of dramatic outbursts that rewrite our understanding of how giant comets behave. The first signs of activity will likely appear when the object crosses the frost line, the distance where solar radiation becomes strong enough to vaporize frozen gases. For most comets, this happens around Jupiter's orbit, but 2014 UN-271 is so massive that heat takes longer to penetrate its core, meaning its surface could remain dormant until it's much closer to the Sun. When the thaw finally begins, the sheer volume of ices sublimating could trigger explosive jets of gas and dust, launching plumes thousands of miles into space. These outbursts might not be steady either. As fresh pockets of volatile material become exposed, the comet could flare unpredictably, brightening by several magnitudes in just hours. The real question is whether these eruptions will make it visible without telescopes. Current projections suggest 2014 UN-271 will reach about the brightness of Pluto at its peak, faint for naked eye viewing but easily spotted with binoculars. However, if it experiences major outbursts like Comet Hale-Bopp did in 1997, it could briefly become a dim but unmistakable smudge in the night sky. Its enormous coma, the cloud of gas and dust surrounding the nucleus, might stretch wider than the full moon, creating a ghostly halo visible even from light-polluted cities. Then there's the wild card: what happens if the comet fractures? Objects this large often contain structural weaknesses from eons of cosmic radiation. As solar heating intensifies, internal pressures could build until entire sections of the nucleus split apart, releasing trapped gases in catastrophic explosions. This scenario would dramatically increase brightness but also create a field of debris trailing behind the main body, a potential hazard for future spacecraft missions hoping to study it up close. Regardless of how it behaves, 2014 UN-271 offers a golden opportunity for science. Every puff of gas it releases carries chemical clues about the early solar system, frozen unchanged for billions of years. Its dust tail will act like a cosmic fingerprint analyzer, revealing minerals that predate the planets. And if it does come from interstellar space, we might be looking at our first chance to study an alien ice giant's composition without sending a probe light years away. The countdown to 2031 has already begun in observatories worldwide. Whether it puts on a dazzling show or remains a subtle telescopic curiosity, this visitor from the outer dark is guaranteed to teach us something extraordinary. The only certainty is that when it arrives, the textbooks won't be the same afterward. Far beyond our solar system, in the constellation Cygnus, lies a star so strange that it made scientists seriously consider whether we were witnessing an alien civilization at work. Officially known as KIC 8462852, but nicknamed Tabby's star after astronomer Tabitha Boyajian, who first studied its bizarre behavior, this flickering sun doesn't just dim slightly like planets passing in front of stars usually do. Instead, its light drops by staggering amounts, up to 22% at times, in chaotic, unpredictable patterns that defy all natural explanations. What makes Tabby's star so eerily fascinating isn't just the dips in brightness, but the shape of those dips. When a planet transits a star, the dimming is symmetrical. The light curve forms a smooth U-shape as the planet blocks the star's glow evenly. But Tabby's star's light curves are jagged, uneven, almost as if something irregular, something artificial were passing in front of it. The most startling theory proposed that we might be looking at a Dyson swarm, a hypothetical megastructure built by an advanced civilization to harvest energy from its host star. Imagine a colossal network of solar panels or habitats orbiting so densely that they intermittently blot out the star's light in these strange geometric patterns. Of course, scientists explored every possible natural explanation first. Maybe it was surrounded by a swarm of comets, but no known comet family could cause such extreme, irregular dimming. Dust clouds, the star's spectrum didn't show the telltale signs. A deformed star, observations ruled that out too. Even a rogue black hole was considered before being dismissed. With each failed hypothesis, the mystery only deepened, leaving that tantalizing, almost taboo question lingering. Could this be evidence of intelligence beyond Earth? The truth, as it often is in astronomy, turned out to be both simpler and stranger. Later studies suggested the star might be consuming a planet, a catastrophic, messy process that could throw up uneven clouds of debris. Others point to intrinsic stellar variability, where the star itself pulsates or sports massive star spots. Yet even these explanations don't fully account for the extreme, irregular dimming. Tabby's star remains an enigma, a cosmic Rorschach test that challenges our assumptions about what's possible in the universe. While it's light years away from the Oort cloud, Tabby's star shares something profound with the strange objects lurking in our solar system's frozen fringe. It reminds us that the universe is far weirder than our textbooks suggest. Whether it's an alien megastructure, a dying planet, or some phenomenon we haven't even named yet, it proves one thing: the cosmos loves to surprise us. And sometimes the most thrilling discoveries aren't the answers we find, but the questions we didn't even know to ask. Deep in the frozen outskirts of our solar system, far beyond the reach of Neptune's gravity, drifts an object that refuses to fit neatly into any category: 2006 SQ372. At first glance, it looks like just another icy body among countless others in the Kuiper belt. But its orbit tells a different story, one so extreme that it blurs the line between asteroid and comet, between native and visitor, between the known and the utterly mysterious. This strange traveler follows a path unlike anything else in our cosmic neighborhood, a stretched, elliptical orbit that takes it from the inner solar system all the way out toward the hypothesized inner Oort cloud. Picture a cosmic slingshot. At its closest approach, 2006 SQ372 swings within the orbit of Neptune, only to be flung outward to distances over 2,000 times farther than Earth is from the Sun. A single journey around the Sun takes this solitary wanderer roughly 22,500 years longer than all of recorded human history. What makes this object so baffling isn't just its extreme orbit, it's the way it behaves along the way. Most bodies following such elongated paths become active comets when they near the Sun, sprouting glowing tails as their ices vaporize. But 2006 SQ372 stays stubbornly inert, showing no signs of outgassing or a coma despite its comet-like trajectory. It's as if someone took the orbit of Halley's Comet and erased all the telltale activity, leaving behind a silent, enigmatic rock drifting through the dark. Astronomers suspect this cosmic oddball might be a messenger from the inner Oort cloud, a region of icy objects thought to exist between the Kuiper belt and the more distant spherical Oort cloud. Unlike its more famous cousins in the Kuiper belt, which have relatively stable orbits, 2006 SQ372 seems to have been nudged inward by gravitational interactions, possibly with Neptune or some unseen perturber. Its current path suggests it's in transition caught between the outer solar system's orderly dance and the chaotic realm of the Oort cloud's drifting icebergs. Theories about its origins are as intriguing as the object itself. Some researchers propose it could be a displaced centaur, an icy body from the outer solar system that got tossed into this bizarre orbit during the planet's early migrations. Others suggest it might be a rare Damocloid, a type of asteroid with a comet-like orbit but no cometary activity, possibly the burnt-out remnant of a long-dead comet that exhausted all its volatile materials. Then there's the tantalizing possibility that 2006 SQ372 is giving us our first glimpse of a whole new population of objects, ones that bridge the gap between the Kuiper belt and the Oort cloud. If confirmed, it could mean our solar system's frozen fringe is far more dynamic than we imagined, with objects constantly being exchanged between these distant zones like cosmic freighters on an invisible highway. Every observation of this strange traveler adds another piece to the puzzle, but the full picture remains frustratingly out of reach. Is it a refugee from the Oort cloud, a relic of planetary migration, or something else entirely? For now, 2006 SQ372 keeps its secrets close, drifting silently along its unimaginably long path, a cosmic question mark reminding us just how much we still have to learn about the dark edges of our own solar system. In the vast, uncharted wilderness beyond Neptune, where the sun's light fades to little more than a distant spark, astronomers have spotted something remarkable. A tiny world so far away it redefines our understanding of the solar system's edge. Nicknamed FarFarOut, this dim speck of reflected sunlight currently holds the record as one of the most distant known objects orbiting our star. At its farthest point, it drifts an astonishing 132 times farther from the Sun than Earth, so remote that a single radio signal sent from Earth would take over 3 days to reach it. What makes FarFarOut so fascinating isn't just its distance, it's the sluggish way it moves against the starry backdrop. Unlike closer objects that zip across telescope views, this celestial recluse takes weeks to show even slight movement, crawling through space at a pace that mirrors the languid drift of Oort Cloud objects. That glacial motion tells astronomers something critical. FarFarOut isn't just far away. It's likely bound by an extraordinarily loose gravitational tether to the Sun, skirting the very frontier where our solar system's influence begins to wane. The discovery, made in 2018, was almost accidental. Astronomers were actually searching for the hypothetical planet 9 when their telescopic scans revealed this faint anomaly. At roughly 140 kilometers wide, FarFarOut is too small to qualify as a dwarf planet, yet its existence challenges assumptions about how objects behave at these extreme distances. Most surprising is its orbit, a stretched, lopsided path suggesting it's been gravitationally nudged by unseen forces. Some researchers propose interactions with Neptune billions of years ago might have flung it outward, while others speculate it could bear the scars of a close encounter with a passing star during our solar system's chaotic infancy. Then there's the puzzle of its surface. At temperatures nearing absolute zero, any ices on FarFarOut should be frozen harder than steel. Yet spectral hints suggest traces of methane, a volatile compound that usually evaporates quickly in space. This raises tantalizing questions. Could FarFarOut have somehow retained primordial ices since the solar system's formation? Or is its methane being replenished by some unknown internal process? Every answer we seek only leads to deeper mysteries. Perhaps most intriguing is what FarFarOut implies about the Oort Cloud's true scale. Current models suggest this object might reside in the inner Oort Cloud, a hypothetical transition zone between the Kuiper belt and the more distant spherical shell of icy bodies. If confirmed, its orbit could act like a cosmic yardstick, helping astronomers map the blurred boundary where the Sun's dominion fades into interstellar space. As telescopes grow more powerful, more FarFarOuts will likely emerge from the darkness, each one a frozen time capsule holding secrets about our solar system's formation. For now, this distant wanderer serves as a humbling reminder. Even in our own cosmic backyard, the most extraordinary discoveries are still waiting in the dark. In the spring of 1997, a celestial visitor lit up the night sky so brilliantly that even city dwellers could spot it with ease: comet Hale-Bopp. This icy wanderer didn't just put on a show, it shattered expectations, glowing nearly 1,000 times brighter than Halley's comet had a decade earlier. What made Hale-Bopp so spectacular wasn't just its luminosity, it was the mystery behind that brilliance. Most comets of its kind originate in the distant Oort Cloud, where they remain frozen relics until gravitational nudges send them sunward. But Hale-Bopp behaved differently from the moment it was discovered 2 years prior, already active at Jupiter's distance, an unheard-of phenomenon that hinted at something unusual lurking beneath its surface. The closer it got, the more puzzles emerged. While typical comets have nuclei measuring a few miles across, Hale-Bopp's core stretched an estimated 25 to 40 miles wide, making it one of the largest ever recorded. This colossal size meant it carried enough volatile ices to sustain spectacular outbursts for months, but that didn't fully explain its hyperactivity. Astronomers soon noticed twin jets of gas erupting from its nucleus in spiral patterns, suggesting an irregular rotation or possibly even a binary structure, two loosely connected chunks spinning in tandem. Some researchers speculated that its interior might harbor exotic ices like carbon monoxide, which vaporize at much colder temperatures than water ice, fueling its early activity. Then came the darker chapter in Hale-Bopp's story, the unwelcome association with the Heaven's Gate cult, whose members tragically saw the comet as a celestial signpost to a higher existence. While this bizarre footnote captured headlines, scientists were grappling with a far more profound question. Was Hale-Bopp a pristine relic from the solar system's birth or something rarer? Its chemical composition offered clues: unusually high levels of deuterium, a heavy isotope of hydrogen, in its water-ice matched ratios found in interstellar clouds, suggesting it might have preserved primordial material unchanged for 4.5 billion years. Even as it faded from view, Hale-Bopp left a trail of unanswered questions. Why did its dust tail show such complex structures, including mysterious hoods and streamers? Could its extreme brightness hint at a capture from another star system, much like Oumuamua decades later? And most intriguingly, when might we see another of its kind? Current estimates suggest Hale-Bopp won't return for another 2,300 years, a sobering reminder that some cosmic spectacles are truly once in a lifetime. Its legacy endures not just in scientific journals, but in the memories of millions who looked up in awe, witnessing a fragment of the solar system's deepest past blazing across the modern sky. What Hale-Bopp taught us is that even familiar phenomena, comets after all, have been recorded since antiquity, can still upend our expectations. Its sheer scale, its stubborn hyperactivity, its chemical fingerprints, all whispered of a cosmos far more dynamic and strange than our textbooks dared to suggest. And somewhere out there in the Oort Cloud's frozen depths, others like it may be waiting, their icy hearts ticking silently until gravity calls them home. When astronomers trained their spectrometers on Hale-Bopp's glowing coma, they uncovered a chemical fingerprint unlike any other comet in recorded history. Mixed among the expected water vapor and dust were traces of argon and molecular nitrogen, gases so volatile they shouldn't have survived in a comet that spent billions of years in the deep freeze of the Oort Cloud. Their presence was like finding ice cubes in a desert, a glaring anomaly that forced scientists to reconsider where and how this cosmic traveler had formed. Argon, in particular, became the smoking gun. This noble gas exists in two forms in space: a lighter version that vaporizes easily and a heavier isotope that clings tighter to icy bodies. Hale-Bopp's coma held far more of the heavy argon than predicted, suggesting it had formed in an environment cold enough to trap even these elusive atoms. The numbers pointed to a birthplace chillingly distant, somewhere near the frosty outskirts of the primordial solar nebula, where temperatures hovered just a few degrees above absolute zero. At those extremes, even gases we consider permanent, like nitrogen, could freeze solid and become locked in the comet's icy matrix. Then there were the organics. Hale-Bopp's spectrum revealed complex carbon-based molecules, including ethanol and formaldehyde compounds usually destroyed by solar radiation unless sheltered in ultra-cold conditions. The cocktail of ingredients resembled less a typical comet and more an interstellar molecular cloud, the kind that birthed stars and planets. This raised a provocative idea. Hale-Bopp might not have formed in the crowded inner solar system at all, but instead coalesced in the lonely, frigid void beyond Neptune, where chemistry follows different rules. The implications rewrite what we know about comet diversity. If Hale-Bopp formed in this extreme cold, it could mean the Oort Cloud isn't just a uniform shell of similar icy bodies, but a layered archive of the solar system's history, with each comet preserving clues about the specific environment where it originated. Some might hail from the warmer Kuiper belt region, while others like Hale-Bopp could be refugees from the solar system's outermost building site, where temperatures and chemistry created fundamentally different kinds of objects. What makes these discoveries so groundbreaking is how they blur the line between comets and interstellar objects. Hale-Bopp's chemistry overlaps with what we'd expect from free-floating nebulas, suggesting the raw materials of star formation might be preserved in deep freeze within our own solar system. Every time such a comet visits, it's not just a light show. It's a messenger carrying preserved samples from the solar system's darkest, coldest creche. And if Hale-Bopp is any indication, we've barely begun to decode the secrets these icy time capsules hold. Imagine a comet that doesn't act like a comet. No glowing tail, no hazy coma, nothing to betray its presence as it streaks through space. Yet somehow, against all expectations, it accelerates as if propelled by unseen forces. These are the solar system's ghost stories, the dark comets, silent, nearly invisible, and defying the usual rules of celestial mechanics. They might be lurking in the Oort Cloud's shadows right now, rewriting what we thought we knew about these icy nomads. The mystery hinges on their bizarre movement. Normally, objects in space follow predictable paths dictated by gravity alone. But dark comets exhibit what astronomers call non-gravitational acceleration, tiny, unexplained velocity changes that suggest something else is at work. Traditional comets get these kicks from outgassing when sunlight vaporizes their ices, creating jets that push them like natural rocket engines. The puzzle. Dark comets show no visible outgassing, no plume of gas, no dusty tail, no telltale shimmer of sublimating ice. It's as if they're powered by stealth thrusters we can't detect. One leading theory suggests these objects might be cloaked in an unusual kind of ice, materials so volatile they vaporize at temperatures far colder than water ice. Carbon monoxide or carbon dioxide could be sublimating in the faint solar heat, producing just enough gas to nudge the comet forward without leaving a visible trace. Picture an iceberg made of dry ice, silently turning to vapor in the darkness, its whispers of gas too faint for our telescopes to catch. Then there's the Oort Cloud connection. Most dark comets discovered so far have elongated orbits stretching deep into the solar system's fringe, hinting they might be refugees from that distant reservoir of icy bodies. Unlike Kuiper belt objects, which often orbit in a relatively flat plane, these drifters follow tilted, chaotic paths, exactly what you'd expect from objects nudged inward by passing stars or galactic tides. If confirmed, it would mean the Oort Cloud isn't just a static repository of ancient ice, but an active conveyor belt sending enigmatic travelers our way. But the plot thickens. Some researchers propose an even wilder idea. What if dark comets aren't icy at all? A handful exhibit rock-like surfaces in infrared scans, sparking debates that they might be rubble piles coated in ultra-black carbon compounds, their dark camouflage hiding volatile ices beneath. Others speculate they could be burnt-out comets' exhausted husks that once blazed brightly but now only vent gas sporadically through cracks in their crusts. Every discovery raises new questions. Are dark comets rare flukes, or does their stealth mean we've missed a whole population hiding in plain sight? Could they be ferrying organic materials from the Oort Cloud to the inner solar system, seeding worlds with probiotic compounds under our noses? And most intriguingly, what else might be drifting out there, invisible to our current technology, its presence only betrayed by the faintest tugs of physics we don't yet understand? The more we study these phantoms, the clearer it becomes. The Oort Cloud isn't just sending us comets. It's sending riddles wrapped in ice and darkness, each one challenging our assumptions about the boundary between the seen and the unseen. And if dark comets teach us anything, it's that the solar system's quietest corners might hold the loudest surprises. Among the countless asteroids circling our sun, one stands out not for its size or composition, but for its sheer defiance of cosmic convention. Meet 514107 Kuiper, an asteroid that moves like no other in our solar system. While nearly every known object orbits the sun in the same counterclockwise direction, a legacy of the swirling gas cloud that birthed our planetary system, this rogue traveler does the exact opposite. Like a salmon swimming upstream, Kuiper bucks the flow, tracing a clockwise path that makes it one of the most unusual residents of our cosmic neighborhood. The anomaly doesn't stop there. Most asteroids cluster in the belt between Mars and Jupiter or follow relatively flat orbits aligned with the planets. But Kuiper carves a tilted, elongated path that carries it from Jupiter's orbit inward past Mars, all while moving backward against the solar system's traffic. This retrograde orbit is so extreme that astronomers initially questioned whether it could be real, yet repeated observations confirmed this isn't a glitch or a trick of perspective. The asteroid genuinely orbits the wrong way, making it a cosmic rebel on an interstellar scale. So how did this misfit end up in our solar system? The leading theory is as intriguing as it is revolutionary. Kuiper might not be from here at all. Computer simulations suggest this backward orbit is nearly impossible to achieve through normal solar system processes. Instead, researchers propose it could be an interstellar interloper, a wanderer from another star system captured by the Sun's gravity billions of years ago. Imagine a scenario where our young solar system, still embedded in its stellar nursery, had a close encounter with a neighboring star. During that brief cosmic rendezvous, gravitational chaos could have yanked Kuiper from its original home and flung it into its bizarre backward orbit around our Sun. The evidence doesn't end with orbital mechanics. Kuiper's composition adds fuel to the interstellar fire. Unlike most asteroids rich in silicates or metals, spectral analysis suggests this object boasts an unusual mix of minerals, including compounds more commonly associated with environments around red dwarf stars. If confirmed, it would mean we're not just looking at an oddball asteroid, but a preserved relic from an entirely different stellar system. Yet the mystery deepens when we consider its survival. Objects on retrograde orbits face constant gravitational harassment from planets and other asteroids, making their lifetimes astronomically short, at least on cosmic timescales. The fact that Kuiper persists suggests it may have slipped into a precarious but stable gravitational niche, like a cosmic eddy where it can orbit backward without being ejected. Some models even hint it could have been locked into this dance during the solar system's infancy, when planet migrations created temporary gravitational pockets perfect for trapping wayward objects. What makes Kuiper so groundbreaking isn't just its origin story, it's what it implies about our cosmic surroundings. If this asteroid truly is an ancient immigrant, then our solar system's history might be far more dynamic than we thought. Other stars could have left similar fingerprints in our celestial backyard, with captured asteroids and even rogue planets hiding in plain sight. Every backward loop of Kuiper whispers a tantalizing possibility that our solar system isn't just a family of native-born worlds, but a vibrant cosmic melting pot, one that's been collecting interstellar drifters since the dawn of time. Deep in the scattered disk of the Kuiper belt, a slow-turning mystery drifts silently through the dark 2007 or 10, nicknamed Gong Gong after a Chinese water god. This reddish dwarf planet isn't just another icy body on the outskirts of our solar system. It's a living fossil, a relic from the solar system's violent youth that may hold the key to understanding how objects migrate between the Kuiper belt and the distant Oort Cloud. What makes 2007 or 10 so fascinating isn't just its size, though at roughly 760 miles wide. It's one of the largest unnamed worlds in our solar system, but the way it moves. Unlike most dwarf planets that spin once every few hours, this one takes a leisurely 45 hours to complete a single rotation. That sluggish turn suggests a dramatic past. Astronomers suspect it was walloped by a colossal impact, leaving it spinning like a cosmic top winding down. The collision might have also given birth to its tiny moon, Xingqiu, discovered orbiting at a curiously close distance in 2016. Then there's the color, a deep, rusty red that stands out against the pale grays of most Kuiper belt objects. This hue comes from tholins, complex organic molecules that form when methane ice gets bombarded by cosmic radiation for billions of years. But here's the puzzle: 2007 or 10 shouldn't have much methane left. At its distance from the Sun, this volatile ice should have evaporated eons ago unless it's being replenished from within. Some researchers speculate it might hide subsurface reservoirs, occasionally venting methane through cryovolcanoes, a phenomenon we've only seen on a handful of distant worlds. What truly sets this dwarf planet apart, though, is its orbit, a stretched, slanted path that bridges two worlds. While most Kuiper belt objects stay within a relatively flat plane, 2007 or 10's orbit is tilted 40 degrees, carrying it from 33 to 100 astronomical units from the Sun. That extreme trajectory places it in a select group of detached objects, bodies whose orbits can't be explained by Neptune's gravity alone. These wanderers act like celestial waypoints, tracing paths that blur the boundary between the Kuiper belt and the inner Oort cloud. The implications are profound. 2007 or 10 might be a transitional object, a missing link showcasing how icy bodies get scattered outward during the solar system's early chaos. Its orbit suggests it was flung into the deep freeze by gravitational encounters, perhaps with Neptune during the planet's migration, or even with an unseen sibling planet later ejected into darkness. If so, studying its composition could reveal how materials from the Kuiper belt get redistributed to the Oort cloud, seeding the outer solar system with organic, rich bodies. There's another tantalizing possibility. 2007 or 10 could be a refugee from the Oort cloud's inner fringe, captured inward during a stellar close encounter. Its reddish color and possible methane vents mirror traits seen in Sedna and other distant objects, hinting at a shared origin in the coldest reaches of our solar system. Each observation adds weight to the idea that these scattered worlds are cosmic archaeologists, preserving layers of history in their ice and rock. As we piece together the story of 2007 or 10, one thing becomes clear: this isn't just another frozen rock. It's a time capsule from an era when planets ricocheted like billiard balls, reshaping the solar system into what we see today. And somewhere in its slow spin, its rusty surface, and its far-reaching orbit, lies a clue to one of astronomy's biggest questions: how the solar system's outermost reaches became a graveyard of displaced worlds. Among the scattered inhabitants of our solar system's outer darkness, few objects defy expectations quite like 2015 BP 519. This distant wanderer doesn't just orbit the Sun, it does so at a jaw-dropping 54-degree tilt, completely out of sync with the flat disk where planets and asteroids typically reside. While most objects align within a few degrees of the solar system's plane, this cosmic maverick carves a path so steep it loops almost perpendicular to everything else, like a daredevil skier racing down a mountainside while the world spins horizontally below. What makes this extreme tilt so baffling isn't just its rarity, it's the physics required to achieve it. Normally, gravitational interactions with giant planets like Jupiter or Neptune nudge objects into mild inclinations, but 54 degrees is too extreme for those usual suspects to explain. Enter the leading theory, Planet 9. This hypothetical super-Earth, thought to lurk 20 times farther out than Neptune, could be the gravitational puppeteer behind 2015 BP 519's bizarre dance. Simulations show a distant, massive planet with a tilted orbit of its own could slingshot smaller objects into similarly steep angles over billions of years, like a cosmic bowling ball scattering pins in unpredictable directions. But there's another, even wilder possibility. This object might carry scars from the solar system's infancy. When the Sun was young, it likely formed in a dense star cluster surrounded by siblings. A close pass from one of these neighboring stars could have yanked 2015 BP 519 into its extreme tilt, leaving it frozen in this unnatural pose long after the perturbing star drifted away. Alternatively, it might have been born from the collision of two primordial bodies, their violent merger sending the survivor spinning off kilter into this solitary, lopsided orbit. The implications ripple outward. If Planet 9 really is shepherding objects like 2015 BP 519, its gravitational fingerprint could help us pinpoint where to search for this hidden world. Each bizarre orbit becomes a breadcrumb trail leading deeper into the dark. But if stellar encounters are to blame, it suggests the Oort Cloud isn't just a relic of our solar system, it's a museum displaying artifacts from a time when stars brushed past each other like strangers in a crowded galactic hallway. What's certain is that 2015 BP 519 doesn't belong. Its very existence challenges textbook models of celestial mechanics, forcing us to confront how little we understand about the gravitational underworld of our solar system's fringe. Whether it's a pawn in Planet Nine's game, a survivor of interstellar sabotage, or something else entirely, this tilted rebel proves one thing: the universe loves breaking its own rules. And out in the Oort Cloud's chaos, there are doubtless more rule breakers waiting to be found. Just 2 years after Oumuamua's fleeting visit, the universe sent us another interstellar gift, but this time there was no mystery about what we were seeing. 2I/Borisov, discovered by amateur astronomer Gennady Borisov in August 2019, streaked into our solar system trailing a brilliant, unmistakable coma of gas and dust. Unlike its enigmatic predecessor, this traveler looked exactly how scientists expected an interstellar comet to appear: a frozen visitor from another star, finally showing its true colors as sunlight vaporized its ancient ices. The differences between Borisov and Oumuamua couldn't be more striking. Where Oumuamua was dry, rocky, and oddly shaped, Borisov was a textbook comet sporting a fuzzy halo and a distinct tail as it neared the sun. Spectroscopic studies revealed a cocktail of familiar compounds: water ice, carbon monoxide, and cyanogen gas, all sublimating under the sun's warmth. But hidden within that seemingly ordinary profile were extraordinary clues. Borisov's carbon monoxide levels were nearly 3 times higher than anything seen in native solar system. Comets, a smoking gun suggesting it formed in an environment vastly different from our own. Here's why that matters: carbon monoxide freezes at far colder temperatures than water ice. The sheer abundance in Borisov implies its birthplace was either chillingly distant from its home star, perhaps in an equivalent of our Oort Cloud, or orbited a much cooler star than our Sun. Either scenario paints a picture of a planetary system where chemistry plays out under alien rules, producing comets with fundamentally different ingredients. Some researchers even speculate Borisov might have originated around a red dwarf star, where frigid outer regions could stockpile carbon monoxide-rich comets like cosmic deep freezers. Then there's the puzzle of its pristine state. Most comets get cooked by repeated passes near their stars, losing volatile ices over time. But Borisov showed none of that weathering. Its composition suggested a first-time visitor, untouched by stellar heat until its fateful plunge into our system. This unspoiled quality makes it a rare time capsule, offering our first direct sample of materials from another star's planetary nursery. Every molecule vented from its surface carried isotopic signatures that could reveal the conditions of its birth cloud billions of years ago. But perhaps most tantalizing is what Borisov didn't bring. Despite hopes of finding exotic minerals or unfamiliar organic compounds, its basic building blocks, water, carbon, silicates, mirrored those in our solar system. This cosmic similarity hints that the ingredients for planetary formation might be universal, mixed and matched across the galaxy in predictable ways. If comets like Borisov are common, then the raw materials for water, and perhaps even life, could be widespread throughout the cosmos. As Borisov faded into the darkness beyond Neptune, it left behind more than just data. It offered proof that Oumuamua wasn't a fluke, that our solar system is constantly being visited by debris from other stars, most too faint or fast for us to notice. Together, these interstellar nomads suggest we're living in a galactic crossfire, with frozen messengers drifting between stars like cosmic bottle mail. And if Borisov is any indication, the next one might carry even clearer signatures of the alien systems that forged it, if we're quick enough to look. As Borisov raced toward its closest approach to the Sun in late 2019, astronomers watched something extraordinary unfold. This interstellar visitor began to come apart. Unlike the mysterious Oumuamua, which remained stubbornly intact during its brief solar system flyby, Borisov revealed itself as fragile, its icy nucleus cracking under the sun's intense heat. By March 2020, Hubble Space Telescope images showed the comet's core splitting into at least 2 distinct fragments, a dramatic breakup that gave scientists their first glimpse of how interstellar objects might behave under stress. This disintegration wasn't just a cosmic light show, it was a treasure trove of data. The way Borisov fractured suggested its composition differed subtly from most solar system comets. Normally, comets break along pre-existing fault lines, weak points formed during their formation billions of years ago. But Borisov's breakup pattern appeared more chaotic, hinting at structural weaknesses distributed throughout its core. Some researchers speculate this could mean it formed in a lower gravity environment, where ices and dust clumped together more loosely than in our solar system's denser protoplanetary disk. Then there was the speed of its demise. Most comets survive multiple passes near the sun before fragmenting, but Borisov began crumbling almost immediately, a sign it might never have experienced such intense stellar heating before. This fits with the idea that it was a virgin traveler, ejected from its home system early in its history and drifting through interstellar space until our sun's gravity snatched it from the void. The breakup also released a burst of gas and dust, allowing astronomers to analyze fresh material from deep inside the nucleus that had been shielded from cosmic rays for eons. But the most startling clue came from the debris itself. Spectra revealed unusually high amounts of carbon monoxide ice in the fragments, up to 26% more than seen in typical solar system comets. Since carbon monoxide vaporizes at much colder temperatures than water ice, this suggests Borisov's original home was either extremely distant from its star or orbited a much cooler star than our Sun. Either scenario implies planetary systems can produce comets with radically different chemical recipes depending on their birth environment. The fragility of Borisov carries profound implications. If most interstellar objects are this delicate, they might routinely fragment when passing close to stars, leaving behind trails of debris that could eventually seed planetary systems with foreign organic compounds. It also raises questions about survival rates. How many of these visitors crumble before we can study them? And could their breakups explain why Oumuamua seemed so unusual? Perhaps it was merely the robust exception in a universe filled with fragile travelers. As telescopes grow more sensitive, we'll likely spot more interstellar objects and more breaking apart. Each fragmentation offers a rare chance to peer inside these cosmic messengers, unpacking not just their composition but the stories of the alien systems that forged them. Borisov's dramatic end wasn't just a farewell, it was an invitation to look deeper, reminding us that even in destruction, the universe reveals its secrets. Beyond the known planets, in the frigid darkness where the sun is little more than a bright star, something massive may be lurking, a hidden world powerful enough to tug at the fabric of our solar system. Astronomers call it Planet 9, a hypothetical giant whose existence is inferred not by direct observation, but by the eerie alignments of distant objects drifting through the Kuiper belt. These icy bodies don't move randomly, their orbits cluster in ways that defy probability, like compass needles all pointing toward the same invisible magnet. The evidence starts with 6 extreme trans-Neptunian objects whose elongated orbits tilt at similar angles and cluster in space, a pattern with less than a 0.0002% chance of occurring naturally. Then there's the peculiar way some Kuiper belt objects orbit backward or at extreme tilts, behaviors suggesting a gravitational disruptor at least 5 times Earth's mass. Simulations reveal a compelling scenario, a distant planet 10 to 20 times farther out than Neptune, shepherding these smaller bodies into their strange configurations over billions of years. But what exactly is Planet 9? The leading theory suggests a super-Earth, a rocky or icy world up to 10 times heftier than our own, exiled to the solar system's fringes during the chaotic planetary migrations of its youth. Such a planet could explain not just the orbital anomalies, but also the mysterious tilt of the Sun's axis, which may bear the gravitational fingerprint of a massive outer companion. Yet there's a wilder possibility. A handful of physicists propose Planet 9 might not be a planet at all, but a primordial black hole, a relic from the Big Bang no larger than a grapefruit, yet containing several Earth masses. Such an object would exert the same gravitational pull as a super-Earth while remaining virtually invisible. The only clue might be occasional bursts of gamma rays as it devours passing comets or dark matter. The hunt for Planet 9 has already reshaped our understanding of the solar system's architecture. Whether it's a rogue super-Earth, a hidden black hole, or something even stranger, its existence would prove that our cosmic neighborhood still holds epoch-making discoveries. Until we spot it or rule it out entirely, this phantom world reminds us that the most profound truths often begin as whispers in the data, waiting for the right moment to step into the light. Finding Planet 9 is like searching for a single dim light bulb lost in the glow of a city skyline while standing on another continent. The challenges pile up quickly. At an estimated distance of 400 to 800 astronomical units, sunlight reflecting off its surface would be 10,000 times fainter than Pluto, pushing even our most advanced telescopes to their limits. Compounding the problem, its orbit likely takes it sweeping through vast swaths of sky, meaning astronomers can't just focus on one patch of darkness, they have to scan a cosmic haystack stretching across constellations. The Vera Rubin Observatory, set to begin its survey in 2025, might finally tip the scales in this cosmic hide-and-seek game. With an 8.4-meter mirror and the world's largest digital camera, capable of capturing images covering 40 times the moon's apparent size, this Chilean observatory will map the entire southern sky every few nights. Unlike traditional telescopes that target specific objects, Rubin's strength lies in catching subtle changes across enormous areas, perfect for spotting a slow-moving dot that doesn't belong. Its repetitive scanning could reveal Planet 9's telltale motion against background stars, even if the world itself is barely brighter than the faintest galaxies. But Rubin isn't the only hunter in the game. The Subaru telescope in Hawaii has already spent hundreds of hours probing likely orbital paths using its hyper-subprime cam, while NASA's Neowise space telescope scans infrared wavelengths where a cold super-Earth might emit faint heat signals. These efforts use clever tricks to maximize their chances, like targeting the hypothetical planet's predicted perihelion region, where it would reflect slightly more sunlight, or searching during opposition when Earth's position makes distant objects appear momentarily brighter. The real breakthrough might come from an unexpected direction: artificial intelligence combing through old survey data. Machine learning algorithms have recently uncovered overlooked Kuiper belt objects in decades-old photographic plates, suggesting Planet 9's faint signature could already be hiding in existing observations, waiting for the right pattern recognition tool to tease it out. Some teams are even training AI to recognize the unique gravitational disturbances a hidden planet would cause in comet trajectories, an indirect approach that could narrow the search area before telescopes swing into action. Yet for all this technology, the greatest obstacle remains time. If Planet 9 is near its farthest orbital point, current instruments might simply lack the sensitivity to spot it. Astronomers may need to wait years, even decades, for it to drift closer along its hypothesized 20,000-year orbit. But the hunt continues because the payoff isn't just another world added to our solar system map. Finding Planet 9 would rewrite the story of how planetary systems form, showing that giants can be exiled to the darkness and survive. It would prove our cosmic neighborhood still holds epoch-making discoveries, not in distant galaxies, but right here in the frozen dark we've barely begun to explore. Far beyond the scattered disk of the Kuiper belt, drifting in the solar system's frozen no-man's land, lurks an object so distant that sunlight takes nearly a week to reach it, the Goblin. Officially catalogued as 2015 TG387, this icy wanderer earned its nickname not just from its Halloween season discovery, but from the way it haunts the outer solar system like a cosmic specter. With an orbit stretching so far that a single trip around the Sun takes 40,000 years, the Goblin spends most of its existence in near total darkness, only occasionally venturing close enough for us to glimpse its faint, reddish glow. What makes the Goblin more than just another distant curiosity is the peculiar path it traces through space. Like a handful of other extreme trans-Neptunian objects, its elongated orbit clusters with others at a similar angle, a celestial chorus singing in gravitational harmony. This alignment isn't random. Computer simulations show that without an external shepherd, these orbits should scatter like billiard balls over time. Yet here they are, all pointing in the same general direction, as if tugged by an unseen hand. That's where the Planet 9 hypothesis comes roaring back into focus. The Goblin's dance fits perfectly with predictions of how a massive outer world would sculpt the orbits of smaller bodies over billions of years. Picture a hidden planet 10 times Earth's mass, orbiting 20 times farther out than Neptune. Its gravity would act like a cosmic comb, sweeping objects like the Goblin into these strange, clustered trajectories. Every new discovery of an ultra-distant object following this pattern, Sedna, 2012 VP113, and now the Goblin adds another stitch to the tapestry of evidence. But the plot thickens when you examine the Goblin's origin story. Its current orbit is so extreme that it likely didn't form there. Instead, astronomers suspect it was hurled outward during the solar system's chaotic infancy, either by gravitational encounters with Neptune or perhaps by the very Planet 9 we're now searching for. The fact that it survived at all is a minor miracle. Most objects ejected so far would have been lost to interstellar space. That the Goblin remains bound to our Sun, tracing its monstrous loop, suggests it found a precarious gravitational niche where it could persist as a relic of those violent early days. Then there's the composition puzzle. Despite its vast distance, the Goblin shows a surprisingly reddish hue in telescopic observations, a sign its surface has been baked by cosmic radiation for eons. Yet spectral hints of water and methane ice suggest it hasn't been completely sterilized by the cold. Some researchers speculate it might even harbor organic compounds similar to those found on other distant objects, raising tantalizing questions about how widely these life-building blocks are distributed across the solar system's frontier. Every detail we uncover about the Goblin tightens the knot between speculation and science. Its orbit isn't just a curiosity. It's a gravitational fingerprint, one that could lead us to the most significant solar system discovery in a century. Whether Planet 9 is out there or not, objects like this force us to confront how little we truly know about the dark, frozen edges of our own cosmic backyard. And with each new detection, the shadows at the solar system's fringe grow more crowded, more mysterious, and more alive with possibility. Buried in the asteroid belt between Mars and Jupiter lies an oddball that doesn't belong, 1996 PW, a cosmic hitchhiker that may have traveled light years before getting trapped in our solar system. At first glance, it blends in with countless other rocky bodies, but its orbit tells a radically different story. While most asteroids follow relatively circular paths, 1996 PW screams along an extreme elliptical trajectory that takes it from inside Earth's orbit all the way out past Jupiter, a range so vast it defies typical asteroid behavior. This interstellar-looking path is just the first clue to its extraordinary origins. Then there's the composition. spectral analysis reveals 1996 PW is packed with carbon compounds resembling certain types of meteorites but with chemical signatures that set it apart. The real shocker came when astronomers calculated its original orbit. Mathematical models suggest it might have been captured from interstellar space long ago, making it a potential time traveler from another star. Unlike Oumuamua or Borisov, which zipped through our system briefly, this asteroid appears to have been gravitationally snared by the Sun, becoming a permanent resident. What seals the case for its alien heritage is its velocity. Most solar system objects move at speeds governed by our Sun's gravity, but 1996 PW's trajectory indicates it was once traveling too fast to have formed here. The leading theory suggests it was flung toward us during the chaotic early days of a nearby star system, then slowed just enough by Jupiter's gravity to become trapped in its current erratic orbit. Picture a cosmic game of pinball where this carbon-rich rock ricocheted between gravitational fields until our solar system claimed it. The implications are staggering. If 1996 PW is indeed an interstellar immigrant, it means our asteroid belt could be hiding MORE Chinese letter silent witnesses to the dynamic exchange of material between stars. These ancient travelers might carry prebiotic compounds from other planetary systems, raising provocative questions about whether life's building blocks are more widely distributed than we imagined. Every analysis of its surface could reveal chemistry tailored to alien environments, offering glimpses of how planetary ingredients vary across the galaxy. Yet the mystery deepens when we consider its age. Simulations suggest 1996 PW may have wandered the Milky Way for billions of years before being captured, making it older than Earth itself. Its battered surface could preserve scars from radiation and cosmic rays accumulated during its epic journey, a roadmap of its passage through interstellar space. The fact that it survived at all hints that such carbon-rich objects might be tougher than we thought, capable of enduring eons between stars. The discovery of 1996 PW forces us to rethink the boundaries of our solar system's influence. If interstellar visitors can become permanent residents, then the line between native and foreign objects blurs dramatically. Our cosmic neighborhood might be far more diverse than we ever suspected, a melting pot of asteroids with wildly different origins, all sharing the same orbital space. And if this carbon-rich wanderer is any indication, the next one we find could rewrite the story of our solar system's formation entirely. In September 2020, astronomers spotted an object approaching Earth with an orbit so peculiar it immediately raised eyebrows. Designated 2020 SO, this supposed asteroid followed a path almost identical to Earth's own, an extreme rarity for natural space rocks. Most asteroids zip past our planet on wildly different trajectories, but this one moved as if it were locked in a slow cosmic dance with us, matching Earth's yearly journey around the Sun. As telescopes focused in, the truth became clear. 2020 SO wasn't an asteroid at all, but a piece of human history returning home, the discarded upper stage of a 1966 Centaur rocket booster from NASA, a Surveyor 2 moon mission, lost in space for 54 years before gravity brought it back. This cosmic imposter perfectly illustrates how difficult it can be to distinguish between natural and artificial objects in the vastness of space. The rocket body's faint, irregular reflectivity and small size, roughly the length of a school bus, initially fooled detection systems designed to spot near-Earth asteroids. Its strange orbital behavior only deepened the mystery. Like many Oort Cloud objects, 2020 SO exhibited non-gravitational acceleration, tiny velocity changes caused not by gravity alone, but by subtle forces like sunlight pushing against its surface. For natural asteroids, this usually comes from outgassing, but in this case, it was solar radiation pressure bouncing off the booster's hollow metallic shell. The implications stretch far beyond one wandering rocket. If a 50-year-old piece of space junk can masquerade as a celestial body, how many other artificial objects might be hiding in our catalogs of asteroids and comets? Some estimates suggest dozens of lost rocket stages and spacecraft fragments still orbit the Sun, occasionally crossing paths with Earth. More unsettling is what this means for future deep space surveys. As we scan the outer solar system for new objects, our telescopes might accidentally tag human-made debris as primordial Oort cloud bodies, especially as more interstellar probes venture into that realm, potentially leaving discarded components in their wake. 2020 SO also raises fascinating questions about the longevity of space debris in cosmic terms. Exposed to decades of micrometeoroid impacts and solar radiation, its surface weathered into something resembling a natural asteroid's patina. Given enough time, could all artificial objects in space eventually become indistinguishable from their natural counterparts? Some researchers speculate that millions of years from now, alien astronomers studying our solar system might find it impossible to tell which objects were spacecraft and which were always there. A sobering reminder of how human activity might leave permanent, if ambiguous, fingerprints in the geological record of the solar system. The booster's temporary capture by Earth's gravity in 2021 provided a rare opportunity to study how materials behave in space over long periods. Spectroscopy revealed how its aluminum skin had eroded and oxidized, creating spectral signatures that initially resembled certain carbon-rich asteroids. This accidental experiment shows how even our best instruments might misinterpret the composition of distant objects, whether they're century-old rocket parts or genuine Oort cloud interlopers. What began as a curious anomaly ended up teaching us more about space archaeology than anticipated. 2020 SO's journey highlights the growing challenge of cosmic identification as our solar system becomes increasingly cluttered with artificial objects. As we push farther into space, the line between natural wonder and human artifact may blur beyond recognition, a silent testament to how deeply our civilization is beginning to shape not just Earth, but the space around us. Far out in the Kuiper belt, where temperatures plunge to -400 degrees Fahrenheit, spins a dwarf planet that shouldn't be this geologically alive. Kuiper, a 700-mile-wide world named after a Tongva creator deity, defies expectations at every turn. Most objects this distant from the Sun should be frozen dead relics, but Kuiper hosts two astonishing features: cryovolcanoes spewing icy slush, and a delicate ring system that physics says shouldn't survive. This isn't just another icy rock, it's a cosmic paradox rewriting our understanding of how small worlds behave. The rings first caught astronomers off guard in 2022 when Kuiper passed in front of a distant star. Instead of the star's light blinking out cleanly as the dwarf planet blocked its view, telescopes recorded additional flickers, telltale dips revealing something else was obscuring the light. Further analysis uncovered a tenuous ring system orbiting Kuiper, similar to Saturn's but far more mysterious. Rings this far out shouldn't exist. At Kuiper's distance, gravitational forces should prevent icy particles from clumping into rings, instead scattering them into space or compressing them into moons within decades. Yet here they are, stubbornly maintaining their structure. One radical theory suggests Kuiper's rings might be younger than expected, perhaps the remnants of a recent moon shattered by an impact. Another proposes they're stabilized by unseen, shepherd moonlets too small for our telescopes to detect, their gravity corralling the debris into neat bands. The most tantalizing explanation: these rings could be actively replenished by cryovolcanic eruptions, icy geysers spraying fresh material into orbit. Which brings us to Kuiper's second enigma, its cryovolcanoes. Most volcanism requires internal heat, something tiny worlds lose quickly in the frigid outer solar system. Yet Kuiper's surface shows clear signs of past and possibly present eruptions of water, ammonia, and methane slurries. How does it stay warm enough for such activity? The answer might lurk beneath its icy crust. Radioactive elements like potassium-40 could provide just enough decay heat to keep a subsurface ocean liquid, pressurized by the weight of overlying ice. When cracks form, this briny mix could erupt onto the surface like a frozen version of Earth's geysers. Alternatively, Quaoar might experience tidal heating gravitational flexing caused by interactions with its moon, Wewat. Even tiny amounts of friction from these tidal tugs could generate the warmth needed to fuel eruptions. What makes Quaoar truly groundbreaking is what it implies about other distant worlds. If this modest dwarf planet can sustain geological activity and rings, then larger Kuiper belt objects like Pluto and Eris might harbor even more dramatic features. It shatters the old view of the outer solar system as a static deep freeze, revealing instead a dynamic realm where small worlds pulse with unexpected energy. Perhaps most intriguingly, Quaoar's existence suggests that life zones might extend far beyond where liquid water can exist on surfaces. Subsurface oceans warmed by radioactivity or tides could be common, hidden beneath the ice of countless dwarf planets. These dark, salty abysses kept liquid by forces we're only beginning to understand might just be the solar system's most surprising habitats. Quaoar doesn't just challenge textbooks, it opens doors to possibilities we've barely dared to imagine. Among the frozen wanderers of the outer solar system, 2002, a W197 stands out like a cosmic lighthouse, its surface unnaturally bright against the inky blackness of space. This dwarf planet candidate reflects nearly 18% of the sunlight that touches it, making it one of the highest albedo objects known beyond Neptune. Most Kuiper belt and Oort cloud bodies are dark as charcoal, their surfaces weathered by eons of cosmic radiation into a dull, reddish patina. So what makes this particular world shine like a freshly fallen snowbank in the void? The answer likely lies in an unexpected frost methane, frozen so hard it behaves more like a glistening shell than the volatile gas we know on Earth. Spectroscopy reveals this icy veneer blanketing 2002, a W197 surface, creating a mirror-like quality rarely seen at such frigid distances. Normally, methane should have evaporated long ago under the feeble solar radiation out here, yet somehow this object has clung to its icy coat for billions of years. One theory suggests its sheer size, roughly 400 miles wide, gives it enough gravity to hold onto these lightweight molecules. Another proposes that its methane isn't primordial at all, but continually replenished by cryovolcanic activity, with slushy methane water mixtures erupting from deep below and instantly freezing in the vacuum. But the real puzzle isn't just how 2002, a W197 keeps its frost, it's what this implies about the Oort Cloud's hidden population. If objects this bright exist relatively close to the Sun, might there be even more reflective bodies lurking in the cloud's deeper reaches? Some computer models suggest that in the Oort Cloud's extreme cold, not just methane but also nitrogen and carbon monoxide could form stable frosts, creating ultra-bright surfaces on worlds we've yet to discover. These distant ice balls might act like cosmic refrigerators, preserving volatile compounds that vaporize closer to the Sun. The implications ripple outward. High albedo objects could dramatically alter our estimates of the outer solar system's mass. Normally, astronomers calculate sizes based on brightness, assuming a dark surface. They infer large diameters to account for the faint reflected light. But if more objects shine like 2002, a W197, we may have overestimated their sizes, meaning the Kuiper belt and Oort cloud could contain countless smaller, brighter worlds instead of fewer large, dark ones. There's another tantalizing possibility. This frosty sheen might be seasonal. As 2002, a W197 slowly orbits the Sun over centuries, subtle temperature changes could cause its methane to sublimate and recondense in cycles, creating temporary bright caps at its poles, a phenomenon we see on Pluto and Neptune's moon Triton, but never before on something so distant. Watching these changes unfold would require patience beyond human lifespans, but the very idea hints at dynamic processes occurring even in the solar system's frozen attic. What makes 2002 a W197 truly remarkable isn't just its shine, it's the way it challenges our assumptions about survival at the edge. If methane can persist here, what other fragile compounds might endure in the Oort Cloud's shadowy depths? Could complex organics or even probiotic molecules be locked in icy stasis, waiting for a gravitational nudge to bring them sunward? This bright, frosty world offers more than just reflected light. It's a glimpse into the delicate balance of preservation and change in the solar system's most remote corners. Out in the frozen reaches beyond Neptune, two celestial dancers perform a gravitational waltz so bizarre it makes astronomers question everything they know about how binary systems form. 2001 QW322 isn't just a pair of objects orbiting each other. It's a cosmic paradox. These twin worlds, each roughly 80 miles wide, circle one another at a staggering distance of 80,000 miles, over 10 times farther apart than typical binary trans-Neptunian objects. To put that in perspective, if these were Earth and its moon, our moon would be orbiting somewhere near Venus. This extreme separation defies every current model of binary formation. Normally, paired objects in the Kuiper belt either form close together from collisions or get nudged into tight orbits by planetary encounters. But 2001 QW322's loose configuration shouldn't exist. The energy required to keep these equal mass partners gravitationally bound at such ranges is astronomically unlikely, like balancing two bowling balls on opposite ends of a seesaw and expecting them to stay perfectly level forever. The leading theory suggests an ancient gravitational tango with Neptune might be to blame. Billions of years ago, when the ice giant migrated outward, its gravity could have stretched a single rubble pile asteroid into two pieces, flinging them apart while keeping them tenuously connected. Another possibility, this duo might be the survivors of a disrupted three-body system, where a third object was ejected, leaving these two in an unnaturally wide dance. What's even stranger is their reflectivity. Unlike most distant binaries that share similar surface properties, these twins show stark differences, one bright, one dark. This implies they might not have formed from the same parent body, raising the tantalizing possibility they were strangers before becoming partners, captured into this uneasy alliance during the solar system's chaotic youth. Every observation deepens the puzzle. Their mutual orbit is so fragile that passing stars or galactic tides should have torn them apart over the eons. Yet here they are, a living fossil of dynamics we don't fully understand, a reminder that the outer solar system still holds configurations physics says shouldn't exist. If binaries like this are possible, our models of the early Kuiper belt might need rewriting from the ground up. The existence of 2001 QW322 suggests we've only scratched the surface of binary diversity in the darkness beyond Neptune. If equal mass pairs can survive these extreme separations, what other gravitational oddities might be lurking in the Oort Cloud's depths? Every time we find an exception to the rules, we're forced to reconsider just how creative cosmic mechanics can be when left to their own devices in the frozen dark. Among the Kuiper belt's most bizarre residents, 2003 EL61 spins like a cosmic top kicked into overdrive. This dwarf planet completes a full rotation every 4 hours, so fast it's been stretched into the shape of a squashed football, with its equator bulging outward from centrifugal forces. Picture an ice-covered rugby ball hurtling through space, its surface racing at speeds that would fling loose debris into orbit if not for the relentless grip of gravity. What makes this rapid spin even more astonishing is the sheer energy required to sustain it. Most large objects in the Kuiper belt rotate sedately, their movements slowed by eons of collisions and gravitational interactions. But 2003 EL61 defies this norm, whirling with enough force to have likely birthed its own tiny moons from ejected material. Hubble observations revealed two small satellites tracing wide, irregular orbits, fragments presumably flung outward during some ancient cataclysm that sent the parent body into this dizzying dance. The best clue to its origin lies in its icy armor. Spectroscopic studies show an unusually pure water-ice surface, nearly devoid of the dark organic compounds that typically coat distant objects. This gleaming exterior suggests either recent resurfacing by cryovolcanism, unlikely given the dwarf planet's small size, or a cataclysmic impact that stripped away its outer layers, exposing pristine ice beneath. The latter scenario fits perfectly with the spin rate. Astronomers calculate that a grazing collision with another large body could have transferred enough angular momentum to send 2003 EL61 spinning wildly while simultaneously blasting debris into space. But the real mystery is how such an energetic object ended up in the Kuiper belt at all. Its trajectory hints at a violent past, possibly an encounter with Neptune that flung it outward during the solar system's chaotic youth. Computer simulations show that gravitational interactions with the ice giant could have ejected it from the inner solar system, where collisions were more frequent and energetic enough to create its extreme rotation. Alternatively, it might be a refugee from the scattered disk, a population of objects tossed into erratic orbits by past planetary migrations. The implications stretch beyond this one oddball world. If collisions can spin objects this dramatically and hurl them across the solar system, then 2003 EL61 might be just one survivor of a much larger population of reshaped worlds. Its existence suggests the Kuiper belt isn't a quiet graveyard of primordial ice, but a dynamic arena where ancient impacts still leave their mark on the survivors. Every rapid rotation, every elongated shape, whispers of violence frozen in time, a reminder that even in the deepest freeze, the solar system's history is written in movement. In the realm of deep space oddities, 2007 JJ43 stands out like a blood-red beacon against the darkness. This distant Kuiper belt object sports a hue so intense it makes even Sedna's famous ruddy tint look pale by comparison, earning it classification as one of the ultra-red bodies in our solar system. The color doesn't just defy expectations, it screams of chemistry occurring under conditions we've barely begun to understand. The secret lies in Tholen's complex organic molecules that form when simple compounds like methane or nitrogen ice get bombarded by cosmic rays over billions of years. But 2007 JJ43's extreme coloration suggests its surface hosts a far richer cocktail of these substances than anywhere else we've observed. Spectroscopic analysis reveals not just the typical reddish Tholen seen on other distant worlds, but deeper infrared signatures hinting at unusually long chains of carbon-based molecules. Some researchers speculate these could be precursors to the building blocks of life, preserved in deep freeze since the solar system's birth. What's truly puzzling is how such delicate compounds survived this long. At these distances, solar radiation should have bleached or eroded organic materials over time, yet here they are, clinging stubbornly to this frozen world surface. One radical theory proposes that 2007 JJ43 might be coated in a porous, insulating layer of frost, a kind of cosmic styrofoam that shields its delicate chemistry from destruction. Another suggests it could periodically release fresh methane from subsurface reservoirs, replenishing the raw materials for Tholen production as older layers vaporize away. Then there's the orbit. Unlike most ultra-red objects that cluster in specific regions, 2007 JJ43 follows a path that defies easy categorization. Its trajectory hints at a violent past, possibly an encounter with Neptune that flung it outward, leaving it stranded with its peculiar surface untouched by collisions that might have stirred or darkened its coating elsewhere. This isolation could explain its pristine redness, preserved like a museum piece in the vacuum of space. The implications stretch far beyond this one object. If tholins this complex can form and persist in the Kuiper belt, similar or even more exotic compounds might be common in the Oort Cloud's colder depths. Every crimson-hued world we discover pushes the boundaries of where organic chemistry can thrive, suggesting the raw ingredients for life might be more widespread in the universe than we ever imagined. 2007 JJ43 isn't just a colorful curiosity, it's a testament to the solar system's hidden talent for cooking up complexity in the most unexpected places. In the frozen outskirts of our solar system, a cosmic rebel named Niku spins defiantly against the established order. This 300-mile-wide Kuiper belt object doesn't just orbit the Sun, it does so backward, tracing a retrograde path tilted 110 degrees from the plane where planets peacefully circle. Picture a bustling roundabout where every car moves clockwise except one, barreling the wrong way with no regard for traffic patterns. Niku's very name, derived from the Chinese word for rebellious, perfectly captures its celestial insubordination. But Niku isn't acting alone. Deep analysis reveals its orbit clusters mysteriously with 5 other tilted objects, all moving together like a synchronized swim team performing in zero gravity. The odds of this alignment happening by chance, less than 1%. Something or someone appears to be orchestrating this cosmic ballet from the shadows. Enter the prime suspect, Planet 9. The hypothetical giant lurking beyond Neptune could be gravitationally herding these misfits into their strange configuration. Simulations show a distant super-Earth would naturally sculpt such inclined, clustered orbits over billions of years. Yet Niku's orbit presents an intriguing complication. It's tilted even more extremely than predicted by standard Planet 9 models, suggesting additional forces might be at play. Alternative explanations abound. Some scientists propose Niku could be a captured exoplanetesimal, an immigrant from another star system, yanked into our solar neighborhood during the Sun's early days in a dense stellar nursery. Others suggest it might bear scars from the solar system's violent youth, when migrating planets played gravitational pinball with smaller bodies. There's even a wild-card theory that Galactic tides, the subtle pull of the Milky Way itself, could be warping these distant orbits over eons. The real puzzle isn't just how Niku got its tilt, but why it persists. Normally, such extreme orbits should destabilize rapidly, either flattening out or ejecting the object entirely. The fact that Niku and its cohorts maintain their odd dance suggests an unseen hand continually correcting their steps. Whether that's Planet 9's gravity, collective interactions among the objects, or something even stranger remains one of the Kuiper belt's most tantalizing open cases. Every new observation peels back another layer of mystery. Recent measurements suggest Niku's surface appears surprisingly bright for its size, hinting at fresh ice exposed by geological activity or impact. This unexpected youthfulness in such a distant object raises provocative questions. Could tidal heating from an unseen moon be keeping it active? Does its composition include volatile ices that erupt when warmed slightly during its long orbit? Or are we seeing evidence of a recent collision that reshaped both its surface and trajectory? The deeper we probe, the clearer it becomes Niku isn't just an outlier. It's a messenger from the solar system's wild frontier, challenging our models and daring us to look beyond easy explanations. In its defiant tilt and synchronized dance with fellow rebels, we might be glimpsing the gravitational fingerprints of worlds yet undiscovered, or the lingering echoes of cosmic events lost to time. One thing's certain, until we solve this celestial whodunit, the outer solar system's most rebellious resident will keep confounding our expectations. Drifting through the frozen outskirts of our solar system, a frozen world named 2015 RR245, affectionately nicknamed Drac, by its discoverers, charts an orbit so vast that a single journey around the Sun takes 7 centuries. At its closest approach, this dwarf planet candidate still orbits twice as far as Neptune, while at its most distant, it vanishes into the abyss nearly 100 times farther out. A year on Drac spans longer than the Renaissance, the Industrial Revolution, and the entire history of space exploration combined. Yet what makes this icy wanderer truly remarkable isn't just its glacial pace, it's the way its very existence forces us to question where we draw the line between planets and the countless other bodies drifting through space. Drac belongs to an elite club of trans-Neptunian objects large enough to be potentially rounded by their own gravity, a key criterion for planetary status. Estimates suggest it measures roughly 430 miles across, putting it in the same size class as Ceres, the asteroid belt's lone dwarf planet. But unlike Ceres, Drac's elongated orbit carries it deep into the Kuiper belt's no-man's land, where sunlight is so faint it would appear barely brighter than a full moon on Earth. Despite these extremes, Hubble observations reveal a surprisingly reflective surface, hinting at fresh ices like nitrogen or methane that periodically resurface the terrain, hiding ancient craters beneath a gleaming veil. The real controversy lies in how we classify such objects. When the International Astronomical Union demoted Pluto in 2006, they established 3 rules for planethood. The object must orbit the Sun, be massive enough to achieve hydrostatic equilibrium, a nearly round shape, and have cleared its neighborhood of other sizable bodies. Drac easily checks the first 2 boxes, but like Pluto, it shares its orbital realm with countless other Kuiper belt objects. This ambiguity exposes the tension in our definitions. If we applied the same standards rigorously, our solar system might include dozens of planets, from Eris to Haumea to this very wanderer. Some planetary scientists argue the cleared orbit rule is fundamentally flawed, a relic of geocentric thinking that privileges the 8 classical planets while ignoring the diversity of worlds uncovered since. They propose alternative definitions focusing on geophysical traits, active geology, layered interiors, or even weather systems. By these metrics, Drac could qualify, as its reflective surface and possible cryovolcanic activity suggest dynamic processes beneath the ice. Others counter that expanding the planetary club would dilute the term's meaning, rendering it useless for classification. The debate isn't just academic, it shapes how we fund missions, teach astronomy, and conceptualize our place in the cosmos. Drac's 700-year orbit adds another wrinkle. Unlike the orderly, near-circular paths of the 8 planets, its trajectory is a stretched ellipse reminiscent of comets, a relic of gravitational scattering during the solar system's chaotic youth. This begs the question, are planets defined by their current orbits or their origins? If a Mars-sized body were hurled into the Kuiper belt by an ancient collision, would it cease being a planet? There are no easy answers, only the growing realization that nature's complexity resists our neat categories. As telescopes grow sharper, more Drac-like objects will emerge from the darkness, each one testing the boundaries of our terminology. Whether we call them dwarf planets, Kuiper belt objects, or something else entirely, their presence reminds us that the solar system is far richer and stranger than our labels can contain. In the end, Drac's greatest lesson might be this: sometimes the universe doesn't fit into boxes, and that's exactly what makes exploring it so thrilling. In the asteroid belt between Mars and Jupiter, a cosmic detective story unfolded in 2010 when astronomers spotted what appeared to be a comet with a glaring absence. P2010-A2 had no head. Instead of the bright nucleus and fuzzy coma typical of comets, this object trailed a strange, X-shaped debris field spanning nearly 500,000 miles. At first glance, it seemed to defy classification, but the truth revealed something far more dramatic. We were witnessing the aftermath of a never-before-seen asteroid collision, a violent event frozen in space like a fossilized crash scene. What made this discovery revolutionary wasn't just the collision itself, asteroids smashed together all the time, but how perfectly it mimicked the behavior of distant comets. The debris plume formed delicate filaments that curled outward, resembling the dust tails of Oort cloud comets stirred to life by sunlight. Yet this was no icy wanderer vaporizing as it neared the sun. It was a pile of rock and metal shrapnel drifting through the inner solar system. The illusion was so convincing it blurred the line between two fundamentally different cosmic phenomena, proving that chaos in the asteroid belt could wear the mask of an icy interloper from the solar system's edge. Hubble's razor-sharp images unveiled the smoking gun, a lone house-sized asteroid drifting near the base of the debris structure, likely the surviving fragment of the smaller impactor. Calculations suggested the collision occurred in early 2009, when a rock roughly 10 feet wide slammed into a larger asteroid at over 11,000 miles per hour, 5 times faster than a rifle bullet. The energy released vaporized the smaller body instantly and scattered debris into space, creating that eerie X pattern. Unlike comets, whose tails are sculpted by solar radiation, these dust streams followed ballistic trajectories, their paths dictated solely by the physics of the explosion. The implications rippled far beyond the asteroid belt. If a collision could impersonate a comet so convincingly, how many other comets in our solar system might be cosmic frauds? Some researchers now suspect certain Oort cloud oddities, especially those with abrupt outbursts or strange chemical signatures, could similarly be the wreckage of ancient smash-ups rather than pristine icy bodies. It raises the provocative idea that the outer solar system might host its own demolition derbies, with collisions between iceberg-like objects producing debris we've misinterpreted as normal cometary activity. P2010-A2 also offered a rare glimpse into the life cycle of asteroid dust. Normally, tiny particles get swept away by solar wind or drift out of view within months. But this event's debris persisted for years, allowing scientists to study how gravity and radiation sculpt such clouds over time. The filaments twisted into intricate patterns, revealing hidden currents in the solar system's magnetic environment, a celestial ballet no one predicted from rubble. Most astonishingly, the collision debris developed its own temporary moonlets, pebble-sized clumps that orbited within the cloud for weeks before dispersing. These fleeting microsatellites mirrored the way comets sometimes fracture into swarms of smaller bodies, suggesting that fragmentation might follow universal rules whether the material is ice or rock. The parallels were impossible to ignore. Nature reuses its playbook across vastly different environments, dressing up asteroid fragments as comet impersonators when the conditions align. This headless wonder didn't just challenge our definitions, it exposed how much we still learn from cosmic accidents. Every anomalous streak or odd orbit could be hiding a story of violence frozen in time, waiting for us to recognize the signs. And if collisions in the asteroid belt can mimic Oort cloud visitors so precisely, it forces us to ask, what other celestial doppelgangers are we failing to recognize? The universe loves a good masquerade, and P2010-A2 was its most convincing performance yet. For decades, a chilling hypothesis haunted the fringes of astronomy, the idea that our sun might not travel alone through the galaxy, but could have a dark companion responsible for raining death upon Earth at regular intervals. Known as the Nemesis theory, this concept proposed that a dim red dwarf or brown dwarf star orbits our solar system every 26 million years, its gravitational influence dislodging comets from the outer Oort cloud and sending them cascading toward the inner planets. The timing seemed to match up eerily with mass extinction events in Earth's fossil record, including the catastrophe that wiped out the dinosaurs. What made Nemesis so compelling and terrifying was its brutal elegance. The math appeared to fit, as this hypothetical star swung closest to the Sun during its elongated orbit. its gravity would perturb icy bodies in the Oort Cloud, potentially flinging thousands into collision courses with Earth. The result, cycles of devastation written into the geological record like clockwork. For a time in the 1980s, the theory gained traction, fueled by the discovery of iridium layers in sedimentary rock, a telltale sign of asteroid impacts aligned with extinction boundaries. Yet as powerful telescopes scanned the skies, no such star materialized. Infrared surveys like NASA's A Wise mission meticulously mapped our cosmic neighborhood, ruling out any Nemesis-like object within several light years. The theory, once provocative, faded into obscurity, but it left behind a tantalizing legacy. Modern astronomy now recognizes that while our sun might not have a deadly twin, binary star systems are surprisingly common in the Milky Way. Over half the stars in our galaxy have companions, some locked in dances lasting millennia between close approaches. This realization sparked new questions. Could our solar system have once been part of such a pair? Some simulations suggest the Sun may have formed alongside a sibling star that was torn away during the chaotic early days of the Milky Way, when close encounters with other stars were frequent. Others propose that if Nemesis exists at all, it might be a free-floating rogue planet or brown dwarf drifting unseen in interstellar space, only occasionally brushing past our Oort Cloud. The search for distant solar companions hasn't ended, it's evolved. Projects like the Vera Rubin Observatory are scanning the skies not for a single Death Star, but for any faint, slow-moving objects that might influence the outer solar system. The discovery of sednoid objects like Sedna with peculiar orbits has reignited debates about unseen gravitational forces. Could there still be something lurking out there, not a nemesis bringing extinction, but a quiet shepherd subtly shaping the paths of icy bodies? The Nemesis hypothesis may be debunked, but its spirit lingers in our fascination with the unknown. It reminds us that the universe is full of hidden relationships, unseen forces, and the possibility that even our familiar solar system might have secrets waiting in the dark. Whether or not a stellar killer exists, the quest to understand our cosmic neighborhood continues not out of fear, but from an insatiable curiosity about what else might be out there, quietly shaping the destiny of worlds. From interstellar scouts like Oumuamua to the gravitational enigma of Planet 9, these 25 cosmic oddities have rewritten the map of our celestial neighborhood. Each discovery chips away at the simplistic model of a tidy solar system bounded by planets, revealing instead a sprawling, dynamic realm where dwarf planets tumble in elongated orbits, where icebergs of hydrogen drift between stars, and where ghostly dark comets accelerate without visible tails. The Oort Cloud and its neighboring depths aren't just a repository of ancient ice, they're a frontier where the ordinary laws of planetary science twist into something wilder and more wondrous than we ever imagined. Consider the implications. Sedna's 11,000-year orbit hints at unseen gravitational puppeteers, while FarFarOut's record-breaking distance proves our solar system's reach extends far beyond textbook diagrams. The fragile rings of Kuiper defy orbital physics, and the hyperactive spin of 2003 EL61 speaks to collisions violent enough to reshape worlds. Even the artificial masquerade 2020 SO reminds us that the cosmos doesn't distinguish between natural and human-made mysteries. It simply presents puzzles and dares us to solve them. And yet, for all we've uncovered, the most startling realization is how much remains hidden. Current estimates suggest we've mapped less than 10% of the Oort Cloud's vast territory. Every strange object we find, whether it's the tilted rebellion of Niku or the chemical time capsule of 2007 JJ43, whispers the same truth. We're still beginners in understanding our own cosmic backyard. The next great discovery might already be drifting inward, a frozen vagabond carrying secrets from the solar system's birth or even another star, so stay curious. Keep looking up, because beyond the planets, beyond the Kuiper belt, in that uncharted darkness where the sun's light fades to a flicker, the universe is still writing its strangest stories. And the next chapter, it's out there waiting, frozen in the deep, until the moment gravity nudges it into the